When we look at the origin and the development of blood cells, we know that blood cells are all made from the red bone marrow, and they begin as these pluripotent stem cells. Notice that these can become myeloid stem cells, which become all of your blood cell types, including your platelets, your thrombocytes, those formed elements, except for some of your lymphocytes, which come from lymphoid stem cells. So those myeloid stem cells become colony-forming units. So we've got colony-forming unit erythrocytes, megakaryocytes, and granulocytic macrophages, and these are going to become precursor cells. The suffix blast means it's an immature and forming cell. So we've got all these different types of blasts coming from the myeloid stem cells: proerythroblast, megakaryoblast, eosinophilic myeloblast, basophilic myeloblast, myeloblast, and monoblast. And what they're coming from, these stem cells can differentiate into different types, we can see. So that's how we get all these different types of blood cells from just this one pluripotent stem cell and this myeloid stem cell. Focusing a little bit on our erythrocytes, since they are our cell that is the most numerous in blood, they first will become a precursor cell called a proerythroblast, and an immature red blood cell is called a reticulocyte. The very interesting thing about erythrocytes is that they are reticulocytes, which eject their nucleus and any other organelle that gets in the way of them carrying oxygen by the large protein hemoglobin, which is a third of the red blood cell's weight. And after that, it becomes a mature erythrocyte that does not have a nucleus. So you'll see on a slide, they kind of look see-through. Megakaryoblast create these very, very large cells in bone marrow. I think of them like a big platter. So a platter is bigger than a plate if you think of all the other cells like a plate. And getting that platter and breaking it on the ground into little bitty pieces, and those little bitty pieces are the thrombocytes or platelets. Notice you get these mast cells coming from myeloid stem cells. These are a type of cell for immunity that we will talk about a bit with immune system. And then we also have our granulocytes, the eosinophils, basophils, and neutrophils coming also from that same lineages. Monocytes are going to be an agranulocyte, and they can become macrophages, and we should think of macrophages as phagocytes. They go through and they essentially eat up old worn out cells and foreign things. And then finally, the pluripotent stem cell that becomes the lymphoid stem cell can become T, B, and natural killer lymphoblasts. They become T cells, B cells, and natural killer cells, which are very specific types of white blood cell that are involved in specific or acquired immunity. Looking a little bit more at the red bone marrow and the case of erythropoiesis, which we said is the process of making erythrocytes, 99% of the formed elements in blood. We start out with that hematopoietic stem cell, and again, the stem cells may become any other type of formed element. But once it becomes an erythrocyte colony-forming unit, if we see back up here, that is now committed to becoming a red blood cell or an erythrocyte. It becomes a proerythroblast that is stimulated by a hormone, erythropoietin, which stimulates your red bone marrow to make those red blood cells. And they are a third of all the cells in the body. You make about 5.4 million per drop if you're a male, and you have about 4.8 million red blood cells per drop if you are a female, and they enter circulation at about 2 million per second. We'll see they're removed from the spleen and liver. They are first, when released, called reticulocytes. Again, these are cells that are losing their nucleus and other organelles not related to carrying oxygen on hemoglobin, that is the third of the cell's weight. Hemoglobin also is what gives the red blood cells their color. You can measure reticulocytes, and this might show things like successful iron therapy, boosting the production of red blood cells by synthetic erythropoietin. But you should measure about 0.5 to 1.5 of the red blood cells being reticulocytes or immature red blood cells. So hemoglobin is synthesized very rapidly in early erythroblast after they have matured from a reticulocyte. The nucleus shrinks and is ejected with the other organelles to make room for that hemoglobin. And it is mature after those are ejected. So we can see there a sinusoidal capillary from bone marrow that is large enough to let those red blood cells out. So erythropoiesis begins in the red bone marrow. We see that if your blood oxygen decreases below normal range, your kidneys detect this, and this is what releases the hormone erythropoietin. When erythropoietin is released into the blood, it stimulates the red bone marrows to go through the process of erythropoiesis, where you have your proerythroblast, reticulocyte, and maturation into red blood cells, which should be able to carry oxygen and brings the oxygen levels back up, and your kidneys respond by releasing less erythropoietin. Those reticulocytes enter circulation, and it takes 1 to 2 days for a reticulocyte to mature into an erythrocyte. Since they do lack a nucleus and ribosomes, they can't repair themselves, so they live about 120 days. So we said we enter about 2 million per second. About 1% of your red blood cells every day are being replaced. And they do actually have to be replaced pretty often. We said 120 days roundabout, because if you think about it, these red blood cells are moving through the blood system. What you see here is a picture from a light microscope. It's showing a stack of blood cells. They stack up kind of like little plates going through very small capillaries, and we call those stacks rouleaux, Rouleaux. And this is for capillaries that are just small enough that they can fit one red blood cell in diameter at a time. So they stack up to go through there. So we know that as they're contorting and moving around the body, they receive a lot of wear and tear and are not able to repair themselves due to lack of a nucleus or ribosomes. And the hemoglobin is going to be a large quaternary structure. So you've got an iron molecule in the middle of each of those 4 polypeptide chains. So we call each of those hemes, each of those little things that look like Saturn here, a heme. And the heme, as you see here, the molecular structure, has an iron in the middle. And the important thing about that is the iron can reversibly bind to one oxygen molecule. So it's important that it reversibly binds so that oxygen can come off where it is needed. So each hemoglobin can carry 4 oxygen molecules from lungs to your tissue cells.